Hi, this is Green from California. Today, I will be introducing you the idea of designing a Micromouse with suction fan and why and how to make the power supply system more efficient in order to make the robot run properly. Before we start to talk about the vacuum Micromouse design, I have to mention the first four-wheel Micromouse designed by Kato Yusuke in Japan at 2009. His design inspired a lot of other Micromouse players to transfer from two-wheel system to four-wheel system. A wheeled vehicle with vacuum design isn't something new. In fact, it was firstly developed by one of the F1 teams, and the most famous example was Brabham BT46 built at 1978, who was run exceptionally fast to beat other competitors. Unfortunately, it was banned for some safety reason the year after. Vacuum design is also used for RoboChaser at Taiwan, since there's currently no restriction on installing a suction fan on the robot to increase traction force. However, it was banned in Japan after 2011 for safety reasons. Although a lot of Micromouse players designed two-wheel Micromouse with suction fans earlier this century, however, the most recognized four-wheel vacuum design Micromouse is the robot Satan, designed by Utsunomiya Masakazu in Japan. His later version Satan Kai captured the first place at the 2014 All Japan Micromouse competition. As a result, this typical design motivated a lot of other Micromouse players, including me, to build our own four-wheel vacuum design Micromouse. Here is the trend for the latest top 3 international Micromouse competitions. The competitions listed here had vacuum design Micromouse won at least one of the top 3 places. In fact, the top 3 were vacuum design at 2015 All Japan and 2016 APAC competition. Here are the 6 vacuum designs who won the top 3 places at 3 international Micromouse competitions mentioned on the previous page. Other than the two-wheel half-size Micromouse Q, the remaining classic-size mice are all four-wheel design with a suction fan to the front. Why do we want to design a vacuum Micromouse? For a very obvious reason, the extra suction fan can create a vacuum chamber underneath the Micromouse as long as it is well sealed. The vacuum chamber tends to have lower air pressure than the open space outside the fan. Therefore, the pressure differences cause a force pushing down by the atmosphere to the Micromouse, consequently giving an extra support force in order to balance the force for the entire system. Due to the increase of the supporting force based on the simple physics we learned in the high school, which is F equal to mu n, we get additional max friction force as a traction force to prevent the mouse slip out at high speed. Other than advantages, the Micromouse with vacuum requires extra efforts during the design phase. There are certain disadvantages should be considered in order to have them balanced during the design. The first disadvantage is the robot consumes more power since the additional suction fan is installed. Besides, the extra pressure on the wheel shafts will increase the load on the motors who drive the wheels. The second problem is the weight. There is additional weight from the module and the potential size and the weight increase of the battery in order to supply the system with a higher power consumption. The third one is the complexity. There are extra circuits required to drive fan, and the condition for power supply is more complex than before. After I explained disadvantages on the previous slide, here I'm asking, why do we need to design a more efficient power system to supply the robot with suction fan? And here are the reasons. The first one is simply because the robot needs more power supply due to the existence of the suction fan. Also, the load increase of the wheel shaft. The second reason would be the limited space on the robot. Since we can infinitely increase the capacity of the battery in order to give sufficient power to the robot, we have to limit the size and the weight of the battery. It also has something to do with the space of PCB, since we don't have infinite amount of PCB space for thermal polygon in a system with a lot of heat dissipation either. We need to make the power supply IC as efficient as possible to avoid this problem. The last reason is related to second reason. The commonly used LDO regulator is simple but way too inefficient. Since the R emitters are passing a lot of current, it gives the LDO regulator who supplies the R emitter a pretty high load. Due to the characteristics of the LDO regulator, The more we use, the more we will be wasted. On the other hand, people tend to use 5 volts with a serial current limiting resistor along with the N MOSFET to drive the IR emitting circuit. As a result, most of the voltage drops on the current limiting resistor, causing a resistor heating. Furthermore, the voltage divided on those resistors are wasted and straight to heat. Here is the overall looking of a typical power system for a non-vacuum 2-cell LiPo design, where all the devices other than the motor drivers are supplied by a single 5 volts LDO regulator, from an average 8 volt input to 5 volt output. Then a 3.3 volts LDO regulator stays after. All the analog devices are supplied with the same 3.3 volts regulator with an additional LC filter for a more stable supply. Low dropout regulator is the biggest cause of the power wastage, since it simply drops the voltage to the target voltage by converting the dropped voltage to heat, which is very inefficient. Therefore, you can see some models like 7805 LDO regulator has a backplate for optional heat sink. Typically, LDO regulator requires more space for thermal dissipation. Here is an example how much power had been wasted on typical 2-cell LiPo to 5 volts LDO configuration. The average operating battery voltage is about 8 volts. Vout is 5 volt. Power wastage percentage is at least 37.5% by default through the calculation. For my previous Green Giant 4.1 mouse, the current usage range for the 5 volt LDO is from 50 mA to 700 mA. So the worst case power wastage is 2.1 volts. Although this is peak power usage, but this is enough power to make the 5 volt LDO regulator really hot. The other component that wastes a lot power is the IR emitter driving circuit. This type of circuit is simple to build and easy to control. For the configuration of my previous Micromouse, I used a 10 ohm current limiting resistor to make the pulsing current for IR emitter at about 500 mA. According to the diagram provided on the datasheet of SFH4545, the IR LED drops 1.8 volts at 500 mA. Therefore, we can calculate the voltage drop on the current limiting resistor, also its power wastage. We can clearly tell from the results that the efficiency of the IR emitting system is very low. Here comes the question, how do we fix it? Through my research, turned out I only found one suitable solution to make this happen, which is DC-DC switching technology. Here is a new power regulator IC for 5 volt system LMZ21701 on my latest Micromouse Green Giant 5.1V. It has a very high efficiency for power conversion. Even though I use this IC converts from 3-cell LiPo battery to 5 volts, the typical efficiency can still remain at about 90%, based on the results on the diagram provided by datasheet. This buck converter IC is also very small, to help me to save valuable space on PCB. The configuration is also quite simple since there's only 8 pins, and that the remaining components, including the inductors, are included within the package. Now we fixed the problem of 5 volt supply system, and then let's look at the other problem I mentioned before, the IR emitting system. By making this part more efficient, I had 3 approaches to make this happen. They are lower power supply voltage, lower current limiting resistance, and a lower overall current. My solution is simply use another highly integrated buck converter IC, LMZ10501, to switch from 5 volt to 2 volt. Similar as LMZ21701 I used for 5 volt system, LMZ10501 is very easy to configure too, since it also has 8 pins. Because the target voltage is 2 volts based on the data diagram provided by datasheet, the efficiency remains above 90% most of the times. In order to make it more straightforward, here I calculate the typical efficiency for the new driving system for IR emitter, where the current is dropped to 333 mA instead of 500 mA. At 333 mA current, the SFH4545 drops 1.75 volts, therefore only 0.25 volts is dropped on the current limiting resistor. There's no need to make the supply voltage running at an even lower voltage such as 1.8 volts, since we need to leave some headroom to cover any imperfections of the system. Now the efficiency for the new system is 87.5%, compared to previous one at 36%. This is a significant boost. Because the suction fan is used, and the rated voltage for the fan motor is 3.7 volt, a dedicated power supply system seems to be necessary. The picture to the right is the circuit of the suction fan driving system. In this case, I designed a supply system that can provide up to 3 amp at 3.1 volts by using another buck converter with higher current supply capability. A dedicated power supply also minimizes the chance to have interference between components who share the same power system. Because the V-in is 13 volts, Vout is 3.1 volt. According to the datasheet, we can predict the efficiency is about 90% most of the times. Here is a diagram of the new power system on my current Green Giant 5.1V mouse. You can find there a lot more power ICs are used. However, as a trade-off, the system efficiency is significantly higher than before. The amount of power saved can be used by motors and the fan in order to achieve a noticeable amount of performance improvement even with the same battery. Apparently, nothing is perfect, and everything has its own two sides. A massive populated DC-DC design also brings a lot of problems. First one is the switching noises caused by DC-DC operation. The solution to solve it will be very easy. Just simply add more capacitors to increase the capacitance and reduce the ESR, although it will require more PCB space. We can also isolate the supply and the ground path for each switching ICs by minimizing the probabilities for them to interfere between each other. In addition, LC filters can be added at any spot that are necessary. As what I mentioned, although those DC-DC ICs tend to take smaller space, but the extra capacitor requirement would cancel out the benefit. Also, since we need to use more power ICs than before, normally more PCB space requirement is expected. There are also some radiation issues exist that requires extra consideration for the design. In this case, more researches for how to draw a proper circuit for DC-DC power supply will be recommended to make a properly working circuit for your robot. The last part is a demo. The demo here is to show the capability of a vacuum Micromouse at a straight and it turns compared to a mouse without a suction fan at 2016 APEC, who access the same fastest path.